Welcome to Engineering Science and 4. If you are new here, I will advise you to subscribe. I usually post content of this nature that can be of great use to you, especially when preparing for your exam. Today's presentation is going to be on shear force and bending moment diagrams. It is really important for you to be able to fully understand how to do this, because in your exam you will most likely get a question of 15 to 20 marks on this subject. Let's begin. First, we're looking at a beam that is loaded with 2-point loads. The one is 80 newtons and the other one is 30 newtons. And also you have the two supports, okay? So the left support is called L and the support on the right is R. And you are given also the location of these forces on the beam. So the beam has a length of 10 meters and you can see where each load is acting. Another question that you have is to draw a shear force and bending moment diagram for this loading case. And so how are you going to do that? So this is the beam that we have. So in order for us to be able to draw the shear force diagram and the bending moment diagram, the first thing that we need to do is to find the reactions, okay? So we need to determine what is the magnitude of L and what is the magnitude of R. And to do that, you can do two moment equations, or you can do one force equation and one moment equation. And this is what I prefer because you are less likely to make mistakes when you do one force equation and one moment equation. I have seen from my experience that when students try to do two moment equations, they actually tend to make more mistakes than if they did one force equation and one moment equation. And so my purpose is to actually try to make things as easy for you as possible, and therefore I am going to go for the approach that is the one with the least chances for you to make a mistake, okay? And so we will do one force equation and one moment equation. And so the force equation is this one. So basically we're saying that the sum of the forces that are pointing up must be equal to the sum of forces that are pointing down. For equilibrium, that is what you want, okay? You want the forces to be balanced. And so if you look at this beam here, the forces that are pointing up is this one, L, and that one here, R. And so the sum of those forces, R plus L, must be equal to the sum of the forces pointing down. The forces pointing down, you have this one 80 newtons and that one 30 newtons. And so if we do that, this is what we will get, okay? R plus L, this is the sum of the forces that are pointing up, must be equal to the sum of the forces that are pointing down, which is 30 plus 80. Okay, so R plus L is therefore equal to 110. So this is the first equation that we will use in solving for R and for L, okay? It's a force equation. We just say the forces pointing up, the sum of the forces pointing up must be equal to the sum of the forces pointing down. Now, the second equation that will be useful in determining the reactions is a moment equation, okay? And here we will say the sum of clockwise moments must be equal to the sum of anti-clockwise moments. And we will take our moments about the support L, okay? So we will take our moments about the far left end of the beam, okay? And so we're taking our moments about L, and we say the sum of clockwise moments must be equal to the sum of anti-clockwise moments. So now, which are the forces that will create a clockwise moment? So if we're taking our moments about L, you can imagine that you can imagine this beam to be a ruler, and then you pin it here with your finger, because that is where we're taking our moments. Now, if you apply a force in the direction of the 80 Newton force, will the ruler rotate clockwise or anti-clockwise? of course, it is going to rotate clockwise. Imagine the beam is a ruler, you pin it here with your finger, and then you push it in the direction of this force. Of course, the ruler is going to rotate clockwise. So this 80 newtons force creates a clockwise moment. And the same is true for this 30 newtons force. Okay, so the sum of the clockwise moments will be the sum of the moments created by the 80 Newton force about point L and the 30 Newton force about L, okay? So the force, the moment of this 80 Newton force about L is simply 80 multiplied by 4. And we will add to that the moment of the 30 Newton force about L, which is just going to be 30 multiplied by 10, because that is the distance between this force and L. And we are taking our moments about L. So the sum of the clockwise moments is this 80 times 4 multiplied by 30 times 10, okay? And this must be equal to the sum of anti-clockwise moments. Now, if you look at this beam here, if we're taking our moments about L, the only force that is creating an anti-clockwise moment is the reaction R. And so this here will be an anti-clockwise moment. Again, you can think of this beam as a ruler. If you pin it at L and you push it in the direction of R, of course, the beam will rotate anti-clockwise. Therefore, this force R is creating an anti-clockwise moment about L. Okay, so the distance is 7, so R times 7 is the anti-clockwise moment that we have. And that is the only anti-clockwise moment that we have, okay? So therefore, the sum of clockwise moment must be equal to the sum of anti-clockwise moments. And in this case, you will have this clockwise moment plus that clockwise moment must be equal to the sum of the anti-clockwise moments, but we only have one anti-clockwise moment due to this reaction R, and that is R multiplied by 7. And so if you do that, then this is what you will end up with, and you will find that R is equal to 88.571 newtons. Once you have the value of R, you can then remember the previous equality that you had on top here, and you will then say L will be equal to 110 minus R, and you know what R is, and therefore you can easily get the value of L. And L will be equal to 21.429 newtons. Okay, so we now have the values for L and R, and so we might as well write them there. And if we do that, then we know now that this force is 21.429 newtons, and that reaction there is 88.571 newtons. Now, what we have to do once we have found the reactions is to draw the shear force diagram. Now, to draw the shear force diagram, the first thing that you will do is to just draw two axes like that, okay? You can see you have a horizontal axis and you also have a vertical axis. So this is the horizontal axis and that here is the vertical axis. Now, the horizontal axis represents the length across the beam, okay? So this axis represents the length across the beam. And the vertical axis, that is the one that represents the shear force. And in this case, it's going to be in newtons because the forces that we have acting on the beam are all in newtons, okay? If the forces were in kilonewtons, then on the shear force axis, the unit would have been kilonewtons, okay? So now, once you have drawn your axis like that, the next thing that you need to do is to look at the points of interest. Now, usually in your exams, they will give you the points of interest, okay? But if they do not give them to you, like in this particular example here, then you need to know that points of interest are points where you have a load applied, okay? So first, the beginning and the end of a beam are both points of interest, but besides the beginning and the end of a beam, you also have every location where a load is applied is a point of interest. So in this case, the beginning of the beam is here, the end of the beam is there, so those will be points of interest. But also, where you have point loads that are being applied, these will also be points of interest. So here is a point of interest, and there also is a point of interest. And so you need to draw vertical lines at all the points of interest, okay? You can see that. So you have one at the beginning of the beam, but this will coincide with the vertical axis. And then one where you have the point load of 80 newtons, here where you have the reaction, which is also a point load on the beam, and then at the end of the beam, okay? These places are locations of interest, and so you need to have vertical lines at those locations. It just makes it easy for you to draw your shear force diagram. Okay, so now the first thing that you need to do now that you want to draw your shear force diagram is to start here at the origin, because for equilibrium, your shear force diagram will always begin at 0, and at the end of the beam, it will also end at 0. Okay, if your shear force diagram does not end at 0, it means that you did something wrong, because if the beam is in equilibrium, your shear force diagram will always end at 0. Okay, so you begin here at 0 and you will also end at 0. So now we begin here at 0. Now if you look at this beam here and the loading case that you see here, you will see that at the beginning of the beam you have a vertical force shooting up with a magnitude of 21.429 newtons. So starting at 0 here, we will go up to 21.429, okay? From 0, we go up to 21.429. This represents that force that you see here. And once you reach this point, now because you have no forces between this point and the 80 Newton force, that means that the shear force will remain at 21.429. Okay, so you will remain there until you reach the place where you have the 80 Newton force. Now, once you reach the place where you have the 80 Newton force, you can see this is a force that is pointing down. So from 21.429, you need to go down by 80 because of this force that is introduced at this location of the beam. So from 21.429, if you go down by 80, you arrive at minus 58.571. Okay, so you just need to do 21.429 minus 80, because 80 newtons is a force that is pointing down. So from 21.429, you need to go down by 80. So you do minus 80, and that leads you to minus 58.571. And between this 80 Newton force and the reaction on the right here, 88.571 newtons, between this force and that force, you have no forces, okay? That means, therefore, that the shear force will remain at this minus 58.571, because between this and this, there are no forces. So you remain there until you come here. Once you reach this location, now you have this reaction R, which is a force that is shooting up. Okay, so from minus 58.571, here you need to go up by 88.571. So from minus 58.571, you need to add 88.571. And so if you do that, minus 58.571 plus 88.571, we add because it is a force that is going up. Where you will arrive is at 30, okay? Minus 58.571 plus 88.571 gives you 30. And once you are at 30, you are here, okay? And between this location and the end of the beam again, there are no forces, so you remain at 30. And then finally, at the end of the beam, you have a point load that is going down. So from 30, you need to go down by 30. So 30 minus 30, you end at 0. And this is a good sign because for equilibrium, you want your shear force diagram to begin at 0 and also to end at 0. Once you've done that, you have drawn the shear force diagram for this particular case. However, you do not stop there. The last thing that you need to do is to shade the shear force diagram, and the way we do that is that we shade between the graph and the horizontal axis. Okay, so this is your graph here. Okay, that's the graph for the shear force diagram, and now you need to shade everywhere between the graph and the horizontal axis. Okay, so this is the last thing that you need to do before completing your shear force diagram. And now the shear force diagram is complete for that loading case. Now let us look at the bending moment diagram. Again, we have our reactions. As you can see, we calculated them earlier. Now we have to draw the bending moment diagram. Again, we will have our horizontal axis and vertical axis. As I said earlier, the horizontal axis is the length across the beam. And in this case, the vertical axis, since we're trying to draw the bending moment diagram, will be the bending moment. And it's going to have units of Newton meters because our forces are all in newtons. If our forces were in kilonewtons, then the bending moment diagram would have units of kilonewton meter. Okay, so in this case, it's Newton meters. And again, we have our points of interest as I explained earlier. The start and the end of the beam are always points of interest, but also everywhere you have a load that is introduced is a point of interest. Okay, so we have that like that. Now we want to draw the bending moment diagram. Now to be able to do that, we're gonna perform cuts on the beam. So we will cut the beam and we'll be cutting it from left to right at all the points of interest. And then we will take the moments about the cut. Okay, so the first point of interest is 80. The other one is here, 80, where you have the reaction, 88.571. Okay, so cutting it from left to right, so we will cut it here and get rid of that, and what we will look at is this, and then we will cut it here, get rid of that, and what we will look at is that. Okay, and so that is what I mean by cutting the beam from left to right. Okay, and then we will take the moments about the cut. Now, when you take your moments about the cut, what you need to understand is that clockwise moments are positive and anti-clockwise moments are negative. That is a convention that we use for us to be able to draw the bending moment diagram. So we're cutting our beam from left to right, and we will take our moments about the cut, bearing in mind that clockwise moments are positive, whereas anti-clockwise moments are negative. And the next thing to remember is that for equilibrium, we also want our moments at the start and the end of the beam to be 0. Okay, so your moment at the beginning of the beam here, or the start of the beam, and the moment at the end of the beam must be 0. This is a condition for equilibrium. So we will not even calculate what is the value of the moment at the start and the end of the beam. We know that those values must be 0. This is a necessary condition for equilibrium. So we will just calculate our moments about the cuts. Okay, very, very important. So the first cut that we're going to make is where you have that 80 Newton force. So we will cut the beam here, do away with this right portion of the beam, and we will just look at this segment of the beam. And so that's what we have there. If you cut the beam here and you get rid of that segment, you will remain with this. Okay, this is what you will have, and the force that is located where you're making the cut falls with the cut, okay? So you do not draw that force there, okay? The force falls with the cut. So the only force that remains is any force that will be on the segment of the beam that you keep, okay? In this case, we're cutting the beam where we have that 80 Newton force. So all of this will fall away, including the force that is acting where the cut is. It will fall away. The only segment of the beam that will remain is what is here and the forces that are acting on this segment. In this case, it's only this one force that is acting on this segment. And so if you look carefully, now if we want to take the moment about the cut is made here. Okay, so if we take our moments about this point, we will only have the moment due to this force, and it is a clockwise moment, okay? And because it is a clockwise moment, remember the convention, clockwise moments are positive. So if we take our moments about the cut, okay, the sum of the moments about the cut, okay, in this case, it's just going to be this L multiplied by that distance, okay? So it's going to be 21.49 multiplied by 4, and it is a positive moment. The reason being that it is a clockwise moment. If you take the moment of that force about this cut, it is a clockwise moment. Again, you can think of the beam as a ruler, and you pin it here with your finger and you try to push it in the direction of the force. You will see that that ruler will rotate clockwise. And so clockwise moments at the cut are positive, and so that is why we have it positive like that. Okay, very, very important. The next cut that we will make is here where you have that right reaction. So we will cut the beam here, get rid of this, and look at the situation that we have there. And remember, every force that is acting at the cut falls with the cut. So this R force is going to fall with the cut. And so if we do that, first, of course, you could already draw the graph for the bending moment, okay? Because we got it here that the magnitude of the moment is 85.716 at the cut. The cut is here where you have the 80 Newton force. And so we know that our bending moment is 0 at the beginning of the beam. And here at this cut, it is 85.716 Newton meters. So it's here. And so from 0 to there, you can just connect them with a straight line, and that will already give you the first segment of your bending moment graph, okay? Now to draw the second segment, back to what I was saying, you now need to make the cut where you have this right reaction. So if we cut the beam here, do away with that and only keep this segment, what we get is this. And I do not have that R force because, as I said, when a force is acting where you're making the cut, it falls away with the cut. And so what you need to do now is to find the moment about the cut of this system that you have here. So if we try to calculate our moments about the cut, what you need to see is that this L force creates a clockwise moment, so its moment will be positive. However, this 80 Newton force creates an anti-clockwise moment about the cut, so its moment must be negative. So we will subtract its moment when we're doing our calculations. So the sum of the moments about the cut will therefore be the moment of this force multiplied by 7, because if we cut the beam here, the distance between this force L and the cut is 7. That is why we multiply 21.429 by 7, and it is positive, okay, because this force creates a clockwise moment. And then we will do minus the moment due to this 80 Newton force. The reason we do minus is because this 80 Newton force is creating an anti-clockwise moment about the cut. And as I said earlier, anti-clockwise moments are negative. And so we do minus 80 multiplied by 3. And so if you do that, you will find that the moment about the cut, that cut, is actually minus 89.997 Newton meters, okay? And so, which means that from here, we are at 85.716 Newton meters, and here we will be at minus 89.997 Newton meters. Okay, so we will draw that line going down to minus 89.997 Newton meters. Okay, and then finally, at the end of the beam, there is no thinking to do there. We know that for equilibrium, the moment at the start and the end of the beam must be zero. Therefore, from here, you will just connect it to zero because of equilibrium. Once you've done that, you pretty much almost done with your bending moment diagram. The last step is to shade between the graph and the horizontal axis. And this is what you see me doing here. You need to shade that. And so that is what you had to do for you to be able to draw the shear force and bending moment diagram for a situation like that. And so this is what we had for the shear force diagram, and that's what we just found for the bending moment diagram. Okay, now a few observations that we need to make. Okay, the first one is that when you only have point loads that are acting on the beam, your bending moment diagram will just be made of straight lines. Okay, somebody will say, what do you mean it will just be made of straight lines? I mean that you won't have a curve in your bending moment diagram, because as we will see very shortly, sometimes you can have a certain kind of load acting on the beam that will create a curve on the bending moment diagram. But that kind of loading is not a point load, okay? But it is a distributed load. So when you only have point loads acting on the beam, you can be sure that your bending moment diagram will only have straight lines, as you see here. Okay, this is the first observation that you need to make and understand. The second observation is that wherever the shear force diagram crosses the horizontal axis, you will have a maximum on the bending moment diagram. And so that maximum can be positive or it can be negative. What do I mean by that statement is that if you look here at this shear force diagram, you will see that it is crossing the horizontal axis here, okay? And it is also crossing the horizontal axis there. So these are the 2 points where the shear force diagram is crossing the horizontal axis. And at these points, if you look at the bending moment diagram, you will see that you have maximum values. Okay, so it can be a positive maximum or a negative maximum, but it will be a maximum values. So remember that when you are drawing your bending moment diagram, that if you are at a location where the shear force diagram crossed the horizontal axis, on your bending moment diagram, that will give you a maximum. Okay, so here at this location, you're supposed to have a maximum on your bending moment diagram, and at that location also you're supposed to have a maximum. Now the maximum can be a positive maximum or a negative maximum. That is just a maximum. That's what I refer to when I say a maximum. It can be a positive or a negative, but just know that that happens when your shear force diagram crosses the horizontal axis. So it crossed it here, okay? So here you have a maximum. Crossed it there, okay? So here you have also a maximum. Although one is a positive maximum and the other is a negative maximum. Let's look at another example. Now, in this example, as you can see, you no longer just have point loads, but you do have one point load and one UDL, okay? When we say UDL, what we mean is uniformly distributed load, okay? So, or you can just say a distributed load, okay? So we have a force of 10 kilonewtons acting on the beam here, and then you have a uniformly distributed load that is acting over this length of 4 meters. And the magnitude of the uniformly distributed load is 20 kilonewtons per meter. And now you have a beam that is loaded like that, and they ask you to draw the shear force and bending moment diagram for this beam. So how will you do that? So this is the loading that we have. So the first thing that we need to do before drawing the shear force and bending moment diagram, of course, is to find the reactions, okay? You need to find the reactions. And so that's the beam that we have. Now for us to be able to find the reactions, the first thing that you need to do when you have a beam that is loaded with a UDL is to find the force that is equivalent to that UDL, okay, for us to be able to find the reactions. So the UDL that we have is a UDL of 20 kilonewtons per meter. And this UDL is acting over a length of 4 meters. So to find the force that is equivalent to the UDL, we need to multiply the UDL by the length over which it is acting. So in this case, the UDL is 20 kilonewtons per meter. If we multiply it by the length over which it is acting, that is 4 meters. So you will have 20 times 4. That will give you the force that is equivalent to that UDL. And that force is 80 kilonewtons. Now that you have that force, you need now to replace the UDL by that force. And so we remove the UDL and we place that force of 80 kilonewtons. Okay, now the big question is, where exactly is this force gonna act? The force that is equivalent to the UDL will act in the middle of the length over which the UDL was acting. If you look at the UDL was acting over this length of 4 meters. So the force equivalent to that will act in the middle of that length. So somewhere in the middle here, which is what we have here. And if you think of it carefully, it will be 2 meters from this point, okay? Because the middle of that length is 2 meters from here, okay? So if you measure from here to where the equivalent force must act, it must give you 2 meters because this whole length is 4 meters. The force equivalent to the UDL will act in the middle of the length over which the UDL was acting. So the UDL was acting over this length. The middle of that length is here, which is just 2 meters from here, or if you want, you could have also said 2 meters from there. And that is where you will have that force that is equivalent to the UDL. And once you have that force there, you can now find the reaction on the left and the reaction on the right using a force balance and a moment balance. Again, I say here it is also possible to find the reactions using two moment balances, okay, but I have found from my experience as a lecturer that using two moment balances cause students to often make mistakes. So it is much easier to do one force balance and one moment balance, okay? And so let us do that. So the force balance simply is to say that the forces that are pointing up must be equal to the forces pointing down. Again, looking at this carefully, you have two forces pointing up, R and L, okay? And then you have two forces pointing down, 80 and 10. So the sum of the forces pointing up must be equal to the sum of the forces pointing down. And this goes to say that R plus L must therefore equal to 90. Okay, R plus L must be equal to 90. Now let us do our moment balance. the sum of clockwise moments must be equal to the sum of anti-clockwise moments. And again, we will take our moments about L, okay? And if you're taking your moments about L, the force L, since it is acting here, will have no moment, okay? Its moment will be zero. That's why we don't even mention it. And so the sum of clockwise moments about L, if you look at this, the 10 kilonewton force will create a clockwise moment about L. The equivalent force here will also create a clockwise moment about L. So we will sum those moments, and that will be equal to the sum of the anti-clockwise moments about L. And we only have one force that causes an anti-clockwise moment about L, and that is R, okay? And so the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments. And so if you do it, this is what you will have: 10 times 1, because that is the distance between this force and this location, plus 80 times, if you measure that whole distance, is 4.5. Okay, the distance between the equivalent force and L is 4.5, and that must be equal to the sum of anti-clockwise moments. In this case, it's only 1, and that will be R times 6.5. And so if you solve that, you will arrive to an expression for R that is equal to 56.923 kilonewtons. Once you have that value for R, then you can solve for L, okay, using the equation that you have on top here. L will therefore be equal to 90 minus R. We know what R is, so you plug in the numbers and you find that L is equal to 33.077 kilonewtons. Now that you have the reactions, you can then now begin to draw the shear force diagram. But before you do that, I know you may be tempted to say, okay, I will draw the shear force diagram using this with the equivalent force here. But if you try to draw the shear force diagram using this, you will make a mistake. That is wrong, to try to use this beam with the equivalent force acting on it to draw the shear force. It is a mistake. The reason being that the beam is not loaded with a point load. That equivalent force, we just use it to be able to find the reaction. But the beam is actually loaded with a distributed load. So you need to use this distributed load picture for you to understand how you will draw the shear force diagram. Do not use this, okay? Because again, I repeat, the equivalent load is only used to be able to calculate the reactions. But in the reality, the beam is not loaded with a point load. It is loaded with a distributed load. So you need to use this now when you want to draw your shear force diagram. Again, I will remind you that the reactions were calculated. The one on the left is 33.077 kilonewtons, and the one on the right is 56.923 kilonewtons. Now, from there, we can draw the shear force diagram. And what I want you to note is that on the vertical axis, the unit this time is kilonewtons, because the forces on the beam are all in kilonewtons. And you also have the horizontal axis, which is just the length across the beam. And as I said earlier, the points of interest are points where you have a point load. So here 10 kilonewton will be a location of interest because we have a point load there. And now when you have a distributed load, locations of interest are the beginning and the end of the distributed load, and any point in the middle that you may want to calculate. Usually I will prefer calculating also the very center of the UDL, but this is useful when you are doing the bending moment diagram. But for the shear force diagram, the point of interest of a UDL is only the beginning and the end of the UDL. So we will draw the beginning of the UDL, the end of the UDL, which is also the end of the beam. Okay, so when drawing the shear force diagram, when you have a UDL, you are only interested in the start of the UDL and the end of the UDL. Okay, that is basically what it is. But if we had a situation where maybe you have a point load in the middle of the UDL, then where you have that point load will also be a location of interest. But in this case, our UDL does not have a point load in the middle of it. So the location of interest when drawing the shear force diagram will just be the beginning of the UDL and the end of the UDL. Now that we have that, we can begin to draw our shear force diagram. So first we are here at 0 because for equilibrium, as I said earlier, the shear force diagram and bending moment diagrams will begin and end at 0, okay? So from 0 here, we have to go up because of this force L that is going up, and that's got a magnitude of 33.077. So we need to go up to 33.077 because of that force. Now, between that force and this force, there are no forces, so we remain there at 33.077. And then from here, being here, because of this 10 kilonewton force that is pointing down, we need to go down by 10. So 33.077 minus 10, that will give you 23.077. And now between this force and the beginning of the UDL, you have no forces here. And so you remain there at 23.077. Now, we are now at this point here where the UDL begins. So, what are you supposed to do now? Well, you need to remember that the force that is equivalent to this UDL is 80 kilonewtons, okay? We calculated that earlier. The force equivalent to this UDL is 80 kilonewtons. So what that means on your shear force diagram is that from the start of the UDL to the end of the UDL, you must go down by 80. Okay, so at the end of the UDL here, you must have gone down by 80 from the 23.077 where you were, okay? So you will do 23.077 minus 80 because the UDL is pressing down on the beam. So it's 23.077 minus 80. That is where you're supposed to end here. So if you do 23.077 minus 80, what you get is minus 56.923, which is a point somewhere here. And that is where you're supposed to end. When you draw the line from where the UDL begins, it begins at 23.077. You must go down by 80 because that is the force equivalent to the UDL. So you must go down by 80 by the time you reach the end of the UDL. So you will do 23.077 minus 80. That gives you minus 56.923. And so from the start of the UDL to the end of the UDL, you must go down by 80. And so because you start at 23.077, going down by 80, you will end at minus 56.923. Okay. And so why do we go down by 80? Because that is the equivalent force to the UDL. It's 80 kilonewtons. And the UDL is pressing down on the beam, okay? So that is why we go down. We were at 27.077. We need to go down by 80 by the time we've reached the end of the UDL. The end of the UDL is here. So by the time we come here, we must have gone down by 80 from where we were. We were at 23.077. Going down by 80, we will reach minus 56.923. And so that is why you have now to draw that line that connects it to this minus 56.923. Once you reach here, you will notice you have the reaction on the right, which is 56.923 going up. Okay, so from minus 56.923, you go up by 56.923, you will end at 0. And this is a good sign because you want your shear force diagram to end at 0. That is a sign that the beam is in equilibrium. The last thing that you need to do, but not least, is to shade the shear force diagram. Students who forget to do that usually lose 1 mark. So you need to shade the shear force diagram like that. And once you have it like that, you're pretty much done with your shear force diagram. Now, let us draw the bending moment diagram. Again, we have this like this, and we have our points of interest like that. Okay, so now here to draw the bending moment diagram, again, you will remember that we make cuts from left to right, sorry. We make cuts from left to right, and we then calculate our moments at the cut. Clockwise moments are taken as positive and anti-clockwise moments are taken as negative. So we're making our cuts from left to right at the points of interest. So the first point of interest is where you have this 10 kilonewton force. That's a point of interest. So if we cut it here, this is what we will have. I hope you can see that. We've cut it at the 10 kilonewton force. We do away with everything there and we just keep this segment here. And the force that is at the location of interest, of course, falls through the cut. And so this is what we will have. If we try to find the sum of moments about the cut, we only have one force, so it's only one moment. And this is a clockwise moment, so it's going to be a positive moment. And this is what you will get, just this force multiplied by that length, and this is what you get. That is the moment about that cut. The second point of interest is here, so we're going to cut the beam there and again find the moment about the cut. So if you cut the beam there and do away with this is what you will be left with, what you see here. And if we try to find our moments about the cut is here. If we try to find our moments about this cut, the sum of moments, remembering that clockwise moments are positive and anti-clockwise moments are negative, then this is what you will get. The moment due to L is positive about the cut because it is clockwise. However, the moment due to the 10 kilonewton force will be anti-clockwise and therefore will be negative, okay, about this cut. And so when you do your sums correctly, this is what you should get. And therefore the moment about the cut at this location here is 67.693 kilonewtons meter. And then I will advise you to also cut the beam in the middle of the distributed load. As I said earlier, usually in your questions, they will tell you exactly where you are supposed to cut the beam. But if they don't tell you, I will advise you to also cut it in the middle of the distributed load. Okay, somewhere there. Okay, you can see here, this line is the middle of the distributed load. So it's just wise to do that. It helps you to have more data when drawing your shear force diagram. And so we will do that. And so if we cut it in the middle, then this is what we will have. And as you can see, we have a segment of the distributed load over a length of 2 meters, okay, because we've cut it in the middle of the distributed load. It is wise to do that if they haven't specified exactly where you need to cut the beam. But if they've told you where to cut the beam, then you just need to cut it at those locations that are given to you. In this case, we were not told where to cut the beam, so I just decided to cut it also in the middle of the distributed load. And this is just so that I have more data on my bending moment diagram. And so if I cut it there and I do away with this segment of the beam and I keep this segment, then this is what I will have. And so I also need to find the moment about the cut for this. Now, what will be the magnitude of this distributed load? I have seen some of my students, they think that when you cut through the distributed load, then the magnitude of the distributed load reduces. It doesn't reduce, it's still 20 kilonewton per meter. Okay, the distributed load is still 20 kilonewton per meter. However, it is now acting just over 2 meters, not over the full 4 meters, but over 2 meters. But the magnitude of this distributed load, although we've cut through it, is still 20 kilonewtons per meter. Okay, and so in order for us to be able to find the moment, the sum of moments at the cut, we need to replace this distributed load by a force that is equivalent to it. In this case, this 20 kilonewton per meter distributed load is acting over 2 meters, so the force equivalent to it will be 20 times 2, and that is 40 kilonewtons. And this force will act in the middle of the length of the distributed load, so it will act at a distance of 1 meter from the right end, okay, because it must be in the middle. And this is the force that we will use when calculating our moment at the cut. Okay, so the sum of moments at the cut, therefore, will be given by this. And as you can see, the clockwise moment that we have is from L, which is this, is positive, but the moment due to the 10 kilonewton force will be a negative moment, and the moment due to this equivalent force to the distributed load, this moment also will be a negative moment because it is anti-clockwise. It's only L that's got a clockwise moment. And so to find the sum of moments at the cut, you will then need to do that sum, and you will find that that is 73.847 kilonewton meter. Okay, very important to understand how we did that. And so now that we have the moments at all the locations of interest, we can go ahead and draw the shear force, the bending moment diagram. Okay, remember that we always begin at 0. At this location here, we have found that the moment is 33.077. So from 0, we will draw a line to 33.077, which is here. And we also found that here, when we cut the beam here, the moment there is 67.693. So from here, we will again draw a line to 67.493, okay? So which is that point there, okay? And here, as you can see, everywhere you have only point loads, it's a straight line on the bending moment diagram. But now it gets interesting where you have a distributed load. Where you have a distributed load on the bending moment diagram, you're gonna have a curve and not a straight line. It's going to be a curve. So because we have a distributed load all through the rest of the beam, so this remaining segment will have a curve. Okay, very important to understand that. But before we get to that, you need to remember what your shear force diagram looked like. And the reason you need to remember how it looked like is because you need to identify where you're supposed to have a maximum value on your bending moment diagram. In this case, you can see, as I said earlier, where the shear force diagram crosses the horizontal axis, that is where you have a maximum on the bending moment diagram. And as you can see here, you cross the horizontal axis on the shear force diagram somewhere at this location, which happens to be somewhere where you have the distributed load. Okay, this here is somewhere where you have the distributed load. However, it's before the middle of the length over which the distributed load is acting. In other words, that maximum value is before the middle of where the distributed load is acting. So it's somewhere here. This is where we will have our maximum value. But we do know that the value of our moment in the middle of the distributed load is 73.847. So here on this line, the moment when we will reach here will be 73.847. But somewhere between here and here, we have the maximum value of the bending moment. Although we do not know its magnitude, but we need to draw our curve in such a way that it goes up to the maximum and then comes down to that value of 73.847, which is the moment that we have here in the middle of the UDL. Okay, so if we do that carefully, this is what we have, and the value that we have there is 73.847. Notice how it is a curve, therefore I used a yellow or somewhat orange line, okay, just to distinguish it from the red lines. The red lines are for straight lines, but the yellow or orange is for the curve, okay? Wherever you have a curve on the bending moment, I will use this yellow-orange line, okay? But if it is red, it means that it's a straight line on the bending moment diagram. So here it's a curve because this segment there is where you have the UDL. And you can see you have a maximum here before you go back to the 73.847 that we have. You have a maximum there because when you look at the shear force diagram, somewhere before you reach the middle of the distributed load, the shear force diagram crosses the horizontal axis, which corresponds to a maximum on the bending moment diagram. Okay, so that's why we go up to that maximum, although we don't know what it is, but we just go up to it and then we go down to the 73.847 that we have here in the middle of the UDL. Okay, so that is the value there. And now from here, we know that at the end of the beam for equilibrium, you must go to 0. So you draw it like that. But again, we use a yellow or orange line, depending on how you see it. Okay, we use that because everywhere you have the UDL, you're supposed to have a curve. It's not a straight line. So when it's a straight line, I say again, I will use a red line, but where your bending moment diagram is a curve, I will use the yellow line so that you can distinguish, okay, when you are studying and preparing. And last but not least, you need to shade, and that will then complete your bending moment diagram. It's important to shade because when you don't do that, you lose 1 mark in your exam. Okay, so always remember to shade between your bending moment graph and the horizontal axis. It is always done that way in engineering. Let's look at another example. Okay, well, before we look at another example, let me just present you the whole solution on one page. Okay, I like to do that because it helps us to draw conclusions and to have more understanding of these matters. And what I want you to see again here is that where the shear force diagram crossed the horizontal axis, that is where we have a maximum on the bending moment diagram. Okay, very important to see. And also where we have the UDL on the beam, on the bending moment diagram, that is a curve. And that's what we will see as a note. Where there is a UDL on the beam, the bending moment diagram will have a curve. So all this segment here will be a curve on the bending moment diagram. Curves, I use the yellow line to distinguish them from straight lines, for which I use red lines. Okay, very important. Now, let us go to the example. Okay, now this is another example. Let's say you walk into your exam and they give you something like that, and you have again to find to draw the shear force diagram and the bending moment diagram for that. Okay, as you can see in this particular example, they have put points where they expect you to cut the beam. Okay, so these will be your points of interest when you are drawing your shear force diagram, and also where you need to calculate your bending moments, okay, where you will cut your beam. Okay, in this case, they've given you the points of interest, and usually in your exam, this is how it's going to be done. They will give you the points of interest where you need to actually do your observations. And so what is really important with this question is that you have a point load that is acting in the middle of the UDL. Somewhere in the UDL, you also have a point load that is acting there. Okay, so how do you do that kind of question? It is not really difficult, and this is what we're going to see now. So this is what we have. So the first thing we need to do, of course, is to find reactions. And to find reactions, we will need to replace that UDL with a force that is equivalent to it. And here you can see we still have the beam with the UDL, but if we need to replace this UDL by a force equivalent to it, we need to first see the length over which the UDL is acting, which is 6 meters in this case. So the force equivalent to it will be 20 multiplied by 6, because this UDL of 20 Newton per meter is acting over a length of 6 meters. And that force will act in the middle of that length. So it will act somewhere here in the middle of this 6 meters length. It will act in the middle there, somewhere there. And so that's what we're going to do. So we get rid of the UDL, we put the force that is equivalent to it, and you can see the UDL was acting over this 6 meters length. So in the middle of it, that will be 3 meters from here. That is where you have the force that is equivalent to the UDL, and it will be equal to 20 multiplied by 6, because the UDL was 20 newtons per meter, and it was acting over a length of 6 meters. So the force equivalent to that will be 20 times 6, which is 120 newtons, okay, not Newton meters. Okay, it was supposed to be newtons, forgive me. This is not the unit, this is a unit for moment. I meant to say newtons here, okay, so this is just a mistake. It is a force that is equivalent to the UDL, so its unit should be newtons. Okay, very important, this is a mistake, it's not Newton meters. And now with that there, we can then go ahead and do our calculations to find the reactions, and we will use one force equation and one moment equation. It's much easier that way. So the force equation is that the sum of forces pointing up is equal to the sum of forces pointing down, and so the forces pointing up are R and L. So R plus L must be equal to 120 plus 70, so R plus L must be equal to 190. And then you have the sum of clockwise moments must be equal to the sum of anti-clockwise moments. Again, we will take our moments about L. So the clockwise moments will be 70 multiplied by that distance, which is 3.5, as you can see. And that will be plus 120 multiplied by that distance there, which is going to be 5. Okay, if you look at it from here to here is 3 plus 2, it's 5. So if we do that, this is what we have. 70 times 3.5 plus 120 times 5 will be equal to the only anti-clockwise moment we have, R multiplied by that whole length, which is 9. 2 plus 6 plus 1, which is 9. And the reason we only have the moment due to R, because R is the only force that is giving us an anti-clockwise moment. If we had another force giving us an anti-clockwise moment, we were gonna add it's the moment of that force to R multiplied by 9. Okay, so we will add something there. But in this case, it's only R that is creating an anti-clockwise moment, so it's R times 9 only. And so with that, you just solve for that, and you find that R is equal to 93.889 newtons. And then you can take this value for R into this equation and solve for L, and you will find that L is equal to 96.111 newtons. Okay, so once you have it like that, then you are fully equipped to be able to draw the shear force diagram. Okay, you did find the reactions, so you are fully equipped to draw the shear force diagram. And by the way, I need to say here that if you want to get access to these notes that I am using in this presentation, you can just contact me using the number in the description, and I will make these notes available to you for free. Okay, so you can get them for free. Just get in touch with me. I will send you these notes that I am using in this presentation. And so now that we have found the two reactions, L and R, we have everything that we need to be able to draw the shear force diagram. And so if we do that, this is what we have, okay? On the vertical axis, you have the shear force in newtons, and on the horizontal axis, you have the length in meters. And so the points of interest here are already given to you, A, B, C, D, E. These are the points of interest. And so you can just draw vertical lines at all the points of interest, and they will serve as in drawing the shear force diagram. Remember, for equilibrium, we need our shear force to be 0 at the beginning. And so from here, we will go up by 96.11 because of that force there. And so going up by 96.111, and we get to that place. And between this force and the beginning of the UDL, there are no forces. And so therefore you remain there at 96.111 until you reach the beginning of the UDL. Now, at this point, I need you to pay close attention. If you look at this UDL, you will see that you have a force that is acting right in the middle of the UDL. And when you have a situation like that, you need to look at this UDL into segments. So the first segment of the UDL that you're going to focus on is this segment that goes from the beginning of the UDL to the 70 Newton force. That is the first segment of the UDL that we will focus on, and we will draw that here. And then the second segment of the UDL that we will focus on is the one that goes from 70 Newton from where the 70 Newton force is applied to the end of the UDL, and that we will draw here. But in between those two segments, we will need to account for this 70 Newton force, which will be here. Okay, and so looking at this first segment of the UDL before the 70 Newton force, you will see that this segment is acting over a length of 1.5 meters. So the force equivalent to that segment of the UDL is just 20 multiplied by that length, 1.5, and that gives you 30. Okay, so 30 newtons is the force that is equivalent to that first segment of the UDL. Okay, 30 newtons. And so what does that mean? That means that we are here at 96.111. For that first segment of the UDL, we will go down by 30. So from 96.111, we need to go down by 30, okay, to come to where we have the 70 newtons force. Okay, we are at 96.111. By the time we finish this segment of the UDL, we must have gone down by 30 because that segment of the UDL is equivalent to a force of 30 newtons. Okay, because it's acting over a length of 1.5 meters, and the UDL is 20 Newton per meter, multiplied by 1.5, it gives you 30. So from 96.111, we must go down by 30 by the time we reach the end of that segment. And so if we do that, this is what we will have, and here, having gone down by 30, we must arrive at 66.111, which is what you get when you do 96.111 minus 30. Okay, we reach here. Now that we are here, we now need to take into account that 70 newtons force. So from 66.111, you need to go down by 70. So 66.111 minus 70, that will lead you to minus 3.889. Okay, this fall is because of that 70 Newton force. So you do 66.111 minus 70, and that leads you to minus 3.889. Once you have taken into account that force, now you need to take into account the remaining portion of the UDL. And this remaining portion of the UDL is acting over a length of 4.5 because the whole UDL acts over 6 meters. So this segment is 1.5 and that segment is 4.5. And the force equivalent to that UDL acting over that length of 4.5 is 20 multiplied by 4.5, which is 90. Okay, so by the time we move from here to the end of that segment, we must have gone down by 90. So from minus 3.889, you do again minus 90 because the UDL is acting down. That will lead you to minus 93.889. Once you reach this point, as you can see, between the end of the UDL and the end of the beam, there are no forces, so you will remain at minus 93.889. You remain at that because you have no forces here. And then once you reach this point, you now have the reaction on the right, which is shooting up by 93.889. So minus 93.889 plus 93.889 will lead you back to 0, which is a good sign because it means that our beam is in equilibrium. Now, last but not least, you need to shade the shear force diagram. Good. Once you've done that, you have drawn the shear force diagram for this particular case. And now let us look at the bending moment diagram. Now to draw the bending moment diagram, again, we have our axis as follow, and we will have also lines at all the points of interest as you see. Again, when you are given points of interest, you just need to consider those points, okay? You don't need to make up points for yourself like I showed you in the previous two examples. And luckily for you, in most of your exams, they will give you points of interest where you need to actually cut the beam and where you need to make your observations. So when they give you those locations of interest, that is where you will pretty much draw these vertical lines and do all the calculations. And so for the bending moment diagram, you will remember that at the beginning of the beam, the moment is 0, and also at the end of the beam, the moment is 0. And now we will perform our cuts at the points of interest. The first point of interest is point B, okay? And so we need to cut the beam there at B. You can see we've made our cut, and then the sum of moments at the cut, in this case it's a clockwise moment, so it's going to be positive, and it's only the moment of one force. So the sum of the moment is just going to be the moment of one force, okay, which is just 96.11 multiplied by 2. And this is what is going to give you here 192.222 newtons meter. Okay, very, very important. And that is the moment that you have here at B. Next, we need to perform the cut at C. And so if we cut our beam at C, this is what we will have. And I want you to notice that you do have a segment of the distributed load. Okay, so we will write its magnitude there. You have that segment of the distributed load, that portion of it, and we've made the cut at C. Okay, we're trying to find the sum of moments at C. We've done away with the rest of the beam. And remember, a force that is acting at a cut falls through the cut when we make the cut. And so now we need to find the magnitude of the moment, the sum of the moments at the cut. Remember, clockwise moments are positive and anti-clockwise moments are negative. So to find the moments at the cut, what we need to do here is to actually replace this segment of the distributed load that's acting over a length of 1.5 meters by the equivalent force to that. And so if we do that, the equivalent force will be 20 multiplied by 1.5. Okay, again, a mistake with the unit here. It's supposed to be newtons. I don't know why I wrote Newton meters. It's a force, it's newtons. Okay, don't get lost because of that. Don't get carried away. This is a force. The unit should have been newtons. And this force that is equivalent to this distributed load will act in the middle of the length over which the distributed load is acting, and so the middle of that length is just 0.75 meters. 0.75 meters from the right. Okay, that's where it is acting. You can see that is the middle of that length, and that load is acting there. And so if we want to find the sum of moments about the cut, the force L will create a positive moment, whereas the equivalent force here will create a negative moment. And so the sum of those moments, therefore, will be like that. Notice the negative sign here, because this force is creating a negative moment. And so once you do it like that, you will find that the moment at C is actually supposed to be equal to 313.889 Newton meters. Okay, very important. And lastly, we need to cut it at D. So if you cut it at D, this is what you will have. Again, you can see that this is the beam, but we've cut it at D and done away with this portion of the beam. And this distributed load here needs to be replaced by a force equivalent to it before we can actually calculate the moment at D. And so it's 20 Newton per meter. If you multiply by 6, that's 120, and that equivalent force will act in the middle there. And so that distance is, of course, 3 meters. And again, I apologize for the wrong unit. Here, I think I was just copying and pasting while I was doing my work, and I did not notice that the unit was actually wrong. Okay, it's supposed to be newtons everywhere, not Newton meters, but newtons everywhere. Okay, and so once you have it like that, you can then calculate the moment at the cut. Notice again that 70 and 120 newtons, these two forces will both have an anti-clockwise moment, and therefore it's negative. So when we're doing the sum, there are moments we will put a negative sign before. So we sum all the moments at the cut at D, and this is what you should get. And the magnitude of the moment at D will be 93.888 Newton meters. Okay, very important. And so having these values, we can go ahead and draw the bending moment diagram. Beginning at 0, when we reach B, at B, the moment is 192.222. So from here to B, it's going to be a straight line, because it's only a curve when we reach the region where we have a distributed load. But before the distributed load and after the distributed load, we're gonna have straight lines in those regions. So going from here to here, 192.222, okay, that's what we will have. But before we start drawing, it's always important to remind yourself of what the shear force diagram looks like. Okay, and so the reason it's good to remember what the shear force diagram looks like is to identify the location where it crosses the horizontal axis. Okay, because where the shear force diagram crosses the horizontal axis, that is where you will have a maximum on your bending moment diagram. In this case, it's going to be here, somewhere here. That is where we have the maximum. And if you look here, that is where we have point C. So the moment at C here is the maximum bending moment that you have on the curve of the bending moment diagram. Okay, because at C, that is also where the shear force diagram crosses the horizontal axis. Okay, now that we've seen that, we will bear in mind that when we reach here, we must be at the maximum. Okay, so from here, as I was saying, we need to go to 192.22. Okay, so starting at 0, we go to 192.22. We are now here, and this is just a straight line. But now we get in the region where we have the UDL, and that is where you're supposed to have curves. So now at C, we know that the bending moment is 313.889 Newton meters, and it's a maximum. So from here, we will go to 313.889, and it's a curve. So we will do it like that, okay? And that is why I draw it with a yellow line or an orange line, so that you can see that there it's actually a curve and not a straight line. At D, again, we calculated the value for the moment at D. It's 93.888 Newton meters. And again, because it's in the region of the UDL, it should be a curve. So from here, we will go to 93.888, but in a curve, okay? Because we are within the region of the UDL, okay? And now here from 93.888, we have to go back to 0 because at the end of the beam, the bending moment must be 0. But as you can see, this region here is not in the region of the UDL. So there is no UDL here, and therefore this region here, you should draw a straight line going down to 0. And then last but not least, you remember to shade your bending moment diagram. And so looking at all that we got for this particular example, this was the shear force diagram, and that of course was the bending moment diagram. Notice that the segment of the beam that is under the influence of the UDL is, when you look at the bending moment diagram on that segment, you have a curve. That's why I used the yellow line. And notice also that the maximum value on the bending moment diagram is where the shear force diagram crosses the horizontal axis, okay? Very, very important. Another example. Now here, this example is particularly interesting because you are given a beam that has got a mass. So when they give you a beam that has got a mass, what do you do? Okay, so you have this beam that is loaded like that with point loads, but you are told that this beam has a mass of 20 kilograms. And luckily for you, they also told you where you need to cut the beam, okay? What are your points of interest? Okay, now this beam has a mass of 20 kilograms. Now, how do you go about drawing the shear force diagram and the bending moment diagram when you are given a beam that actually has a mass? The first thing that you need to do is to convert that mass into a UDL. And the way we do that is to begin by calculating the weight of the beam. So the beam has a mass of 20 kilograms. We know that weight is equal to mass multiplied by G. So if we do 20 times 9.81, we get that the weight of this beam is actually 196.2 newtons. Now, to find the UDL that corresponds to that weight, we need to use this equation. The UDL is equal to the weight of the beam divided by the length of the beam. And so the weight of the beam is 196.2. The length of the beam is 10. So if you divide like that, what you get is that the UDL that corresponds to this weight or that mass for the beam is actually a UDL of 19.62 newtons per meter. And this UDL is going to act over the entire length of the beam. What do I mean by that? Solving this problem is the same thing as solving a problem like this, okay, where you have this and then a UDL that acts over the full length of the beam like that, okay? Very, very important. So when they give you in a question a beam like this, and then they add that the beam has a mass of 20 kilograms, this mass here will allow you to get the weight, and with the weight you will be able to get the UDL that corresponds to that mass using that equation, and that UDL will act over the full length of the beam. So doing this is the same thing as doing that here. So I hope I was clear enough. I am not going to go into the details of drawing the shear force diagram and the bending moment diagram of this, okay? But I will leave that to you as an exercise. But if you do the right thing, you should get a shear force diagram that looks like that and a bending moment diagram that looks like that. But this, of course, I am going to leave to you as an exercise. And so that's all from me today. If you wish to get in touch with me, please use the number in the description. As I said earlier, the notes that I used in this presentation are available for free upon request. So just contact me using the number in the description.